Hi, everyone. So, welcome to this session, and this is going to be a next session about AI in this conference. But I think it's going to be a little bit unusual, because we're not going to talk about LLMs or agents. Well, maybe not in the majority of the talk. Instead, we're going to focus on an aspect that's a little bit more general to machine learning, although also very interesting for the LLMs, so we're going to touch it at the end. So we're going to talk about something called continual learning. And I would like to explain to you this concept and walk with you together through a use case story based on MRI Diagnostics use case. So, hi everyone, my name is Agata Chudzińska. As my last name might suggest, I'm Polish, and this is the way how we traditionally smile on the streets. But I'm working currently at the German AI consultancy in Hamburg, where we are developing projects for a variety of customers from various industries. And I've been working in AI and machine learning over the last 10 years. So as you can imagine, I went through the whole cycle from it's like black magic and get it away from me until we're all AI-first companies right now. So that was quite an interesting journey. But what's interesting here for the rest of this presentation, we have also worked quite a lot with medical-oriented projects and doing projects for the medtech companies. And what do I mean by that? Mainly working with the medical images. So recognizing structures such as bones on an easy example here, more challenging recognizing liver and segmenting even the small veins that you can see here. This was quite difficult task, but super important when it comes to liver resection process, because if you just cut in the wrong place, that can have serious consequences for the patients. And usually also visualizing in three-dimensional space in extended reality, and also doing some additional measurements for surgical planning. But today I would like to tell you a little bit more about one of our most challenging projects, which is connected with something called Focal Cortical Dysplasias, or FCDs. But before we dive deeper into that, a very interesting statistic that maybe you're not aware of, at least I wasn't before I started working on this project, which is that around 50 million people globally, or according to different statistics, around 1% of the global population has epilepsy, which is making it one of the most common neurological diseases globally. And if that wouldn't be enough, each of the epilepsy patients is 24 times more likely to die unexpectedly because of a phenomenon called sudden unexpected death in epilepsy patients. So I think we can all agree this is like quite important issue. So if we explore this topic a little bit more, we'll sooner or later find those FCDs. So what are they? We can see here them under a magnifier glass, so they are some sort of faulty brain tissue, which are very frequent cause of epilepsies, especially those that are pharmacoresistant. Well, the good news here is that they are potentially operable, but it's not so easy to find them. So how do they look like on MRIs? Because it's how we can diagnose them. A short intro, because if you're lucky enough to never have any MRI in your life, so just a short revision. So MRI stands for magnetic resonance imaging, and this is usually a series of pictures. So in our case, it will be 192 pictures in a series. And they are being done by the MRI scanners as the one here. So this is like a tube you get in, it makes loud, strange noises, and it uses magnets and radio frequencies to create very detailed pictures of your inner organs without cutting or anything like that. And you can also use different settings to expose a little bit different features. So, okay, we already have our MRI done, so let's analyze how can we find those FCDs there. So there are a few different features, and they can come in different combinations. So let's not get into too many medical details, but let's just analyze a few of these exemplary features. So one of them is blurring, which you can see here on the right picture. There is also unusual folding of the brain surface, hyperintensities of the gray or white matter, the so-called transmantle sign, which you can see in here, going towards brain center. But not to make things too easy, they can differ in size, in location, and in shape. And those features, they don't always come in there. There can be different variations and different combinations of them. But when things go well, so usually epileptologists, so really the doctor specialized in epilepsy, finds those FCDs. The patients can undergo brain surgery, so this is not AI, this is a real one, and become seizure-free. So it's good news here. So, having all of that knowledge, I have a small task for you, which is, could you tell me which one of these 3 patients, if any, and if yes, which one, has an FCD? So a few seconds for you, and we're gonna make some small voting. Okay, so who thinks it's the patient number 1? Please raise your hand. Okay. Who thinks it's number 2? Okay, and number 3? Yeah, I think number 3 had the majority of the votes, but you're all right. So all of the 3 patients have an FCD. Even though they are not so obvious, like usually in the books, you see some of the features there, well, the reality is a little bit different, so they are quite tricky. So as you can see, this task usually requires a very experienced epileptologist, and as you can imagine, like with any niche knowledge, there are not so many of them. So we thought, how about using AI to detecting it? Like, if you think about, in general, what machine learning, what AI is, and why do you use it, it's actually about detecting some subtle patterns in the data which you know exist. They don't need to be so obvious, so you cannot write rules to detect it yourself. And actually their purpose is to make some knowledge more democratized. So sounds like a perfect case here. So we took a few of our colleagues from our team. We worked together with the biggest epilepsy center in Germany, in Hamburg, and we have even taken a real doctor house to make our chances higher to succeed. So with that, we understood already what the issue was, so we started with the machine learning part. And as usually, we start with the data, because data is everything. So we managed to collect 201 MRI series, so this series of pictures of 201 patients. But we didn't want our model to just recognize FCDs knowing that they are there, so that's why we also added 100 normal MRIs, so of the healthy patients, but as well 50 of the patients with different brain pathologies, so that our model could recognize, okay, there could be some different kinds of pathologies in there. I mentioned to you the different settings of the MRI scanners. So here we use T1, which exposes a little bit more the shapes of the anatomical structures. There is also T2, which focuses on fluids, and FLAIR, which is a special version of T2, which is exposing a little bit more the abnormalities. What was important for us was to take the real world data, right? So we didn't cherry pick the nicest examples of the FCDs, we just took all of them so that it works in practice. And we really wanted to make sure that the FCDs are there. So as I mentioned to you, it's really hard even for doctors and for specialists to find them and to be sure that they are really there. So we checked it with 2 experts. We also, the doctors, analyzed the type of seizures the patients were having, as well as the EEG data, so the electrodes that measure the brain activity, just to be sure that the FCDs were there. If you are in the machine learning world, or you read something about it, or you heard about it, you can say, well, 200 series, that's really not a lot, as for machine learning. And you're right, but I also forgot to mention that this was actually, at this point, the biggest data set in the world, according to any information, that we managed to collect to solve this problem. Well, why is that? Because it's also very hard to annotate this data. So you wanted to make sure to tell machine learning to train it in a way where exactly those FCDs are. So by doing that, we really had to, the experts had to annotate the exact areas where it is. And it was very time-consuming and required really a lot of time of the experts. So we have our data set, so let's go and train some neural networks, right? Well, not really. I mean, we tried doing that, but it turns out that it was not enough data to straight away train the neural network. So we had to take a step back and work with the pre-processing. And we did that in 4 steps. So first of them was the brain tissue segmentation. This is actually a solved task. So we can achieve over 95% of accuracy on it. They are ready neural networks, so let's not spend too much time on that. But we did that for two reasons. So first of it, we wanted to exclude any data like skull, whatever, that was not relevant to our problem. But the second one, it was a prerequisite to use the second method. And the second step is a morphometric analysis. So as I mentioned, it's quite tricky to recognize those FCDs. So the epileptologists came up with some of the methods that help them to recognize them better. So one of them are the methods developed by Dr. Hupert, who exposed a little bit some of the features of the FCDs. And we also, inspired by that, applied the junction and extension. And junction relies on working on the intensities of the pixels, so doing some mathematical operations like standard deviations to expose a little bit more this feature. And extension is quite interesting because it relies on an observation that if you have something slightly blurry and you add more blur to that, it exposes the initial blurring in there. And interesting thing here is that it's also being used to detect some changes done in Photoshop, like when you want to detect like if someone changed this picture, you can also use similar methods to see which of the areas have been changed. I actually don't know if it has any sense right now when everyone's using AI to do it, but just in case. And finally, we put everything as an input. So we took the T1, flare, and the junction extension, did the traditional cropping, padding, and other machine learning methods, and we're ready to go to the next step, which is now training the neural network. So we tried quite many different approaches here. So we trained a lot of different models, and quite interesting observation that we had is that we also used, for example, the transformer network. So you might know transformers because they are also the architecture behind the LLMs, actually. And they are also being used more and more frequently in computer vision. But the interesting fact is, even though that they are newer and like quite popular, etc., they are not always the best choice. At least when it comes to biomedical imaging like this, they are quite frequently different methods that are doing better job than this. So in here we decided to use the UNet architecture, which has quite typical U shape, which you can see here, which worked best in our case. So in very short, how does it work? So it's an encoder-decoder architecture, meaning that in the first step, so in the first part of the U, we're encoding information. So it means we start with the series of our pictures that we have here, and then we're like trying to encode, so create some of the abstract features that are created here in the bottleneck. And then in the decoder, we are trying to get, again, back to either the normal picture, the same picture that we have here, or to segmentation, which here is this quite big FCD. And via training the network in this way, it really needs to learn like what are those super important features that will allow it to, again, come back in a decoder part back to what you want to achieve. And here we also applied the variation decoder. It was just a thing that helped us to not overtrain the model. Evaluation, so how did we do? So we looked at the metrics like object-wise, so we just wanted to know how many of the FCDs we detected correctly, how many not. But also super important, we wanted it to be explainable. So we wanted to know why this model took this decision at the other, and that's why we looked on the voxel-wise metric called dice coefficients. So voxels are basically like we have in 2D pixels, and voxels are the same concept but in 3D. And we actually got quite nice results. I mean, we recognized 70% of the FCDs. Precision was also not bad, so we're not creating so many false positives. Everything's great. So in the medical field, there is additional step that you're doing. So when you have your ready model, you need to do prospective clinical validation or clinical study. So actually, we have taken the next 100 patients that were there in an epilepsy center, and apart from like doing the normal diagnosis of the doctors, they were also testing in parallel our model. And what were the results? So I will guide you quickly through this table and what are the most important information here. So in the middle, we can see the grand truth. So we know that there are 9 FCDs in this data set. So there are 9 patients having it. On the left-hand side, we see that these are the results of 2 neuroradiologists. So doctors, but not super experts in epilepsy. So they managed to recognize 3 of them. And our model on the right-hand side managed to recognize 7, which is super cool, right? I mean, it's quite a good job compared to the doctors. But we're not so happy for a long time, because then we saw what happened here in the below part, which means that the doctors said, created only 5 false positives. So where there is no FCD, for only 5 patients they said there was, but our model did that for 86, which is not a good news. So we wanted to understand what happened. And this is like really, really important. Like whenever you're working with AI, with machine learning, always try to understand why. Even if you're getting the good results, it's always important to understand why the given decision was made. So what were our findings? First of all, in the majority of the cases, when our model said there's 2 or 3 FCDs in one MRI series, it was wrong. But it still can happen. Like, it happens very rarely that one patient is having a few FCDs, but it still can happen, so we couldn't exclude that. And why did they happen? So first of all, it's reacted to the image noise. Like, we wanted to be as close as possible to this real world. Well, we were, but our model also reacted to the image noise, like when patients moved the head or something during the MRI. It was also reacting to similarly looking lesions. So, for example, when there was blurring, which can be one of the aspects of FCDs, well, it detected it, but it wasn't really FCD. Like, it was sharing some of the features, but not all blurring means automatically FCD. And another thing that we saw was that actually our model was recognizing one particular part of the brain, that it was very frequently saying there is an FCD in there. And we analyzed it, and it was because our training data set actually had quite many FCDs in this region. So the conclusion was that we actually had different data distribution. I mean, in reality, I said in the beginning there's like 1% of the global population have an FCD. And our data set was like half of it were FCDs, so it's not something that matches the real distribution. So let's summarize what we have here in the first act. So we have a model that recognizes FCDs quite nicely, but it produces quite many false positives. So it could be useful for the initial screening, like proposing to the doctors, hey, take a look here, because there might be an FCD. But as you know, if you get too many recommendations and they are wrong, you just stop trusting it, right? So it's not optimal. We also have data collected only in one hospital, done by one scanner. So when you would like to apply it to the different scanners, the data can be slightly different, so that's also a potential challenge. Medical data are very sensitive. I know, Mr. Obvious, but this will be important for the next part. And whenever you're working with machine learning in medical fields, there are really strict requirements. I mean, right now it's going to be even worse with all of the AI Acts, etc. Of course, it is important, but it's also a lot of additional work that we need to think about when building this kind of models. So when we're thinking about what we could do better, we dived a little bit deeper into something called continual learning. So before we go into the details, let's have a brief recap so that we're all on the same page of how does the typical machine learning task look like. We actually went through it quickly, so we try to understand the problem first, create the data set, train many different models, and finally we have our idea model, we deploy it in production, and we live happily ever after. I always hope there will be some people laughing on there, so because it's like not really how the real life look. Why? Well, because it's going to be almost always data drift, which means that the data will change its distribution. You're going to have new scanners, like in our case, like go to the different hospitals, the data will just look a little bit differently. If you're building a system in finance for fraud detection, I mean, if you start detecting the frauds, they're going to change their behavior. If you do a recommendation system, people also change their preferences. So the data will always change. You might want to add new classes. I mentioned to you that, for example, we detected FCDs, but there were also some different brain pathologies. So why not detecting at once, like, for example, brain tumors, right? we might want to add a new task. So we are, for example, extracting information. Maybe we would like to make summarizations as well. There will be always bias in the data, no matter how frequently we add new data, how much data we collect, there will be always some kind of bias in there. And all of them will lead eventually to decreasing performance of our models. So what we could do to solve that? So first approach could be transfer learning, or more called nowadays fine-tuning. So let's analyze it using a pet example. So imagine you have pictures of a cat, of a dog, which are your pets, and you would like to automatically have their pictures categorized on your phone, so you just build a small neural network and it works great. But then you buy a guinea pig. And unfortunately, whereas the model recognizes greatly the cats and dogs, it knows nothing about guinea pigs, which is a little bit sad because you would like to have all of your pets being recognized. So you think, how about taking this neural network, because it already knows a lot about pets, like they have 4 legs, they are fluffy, whatever, and just feed it with a few examples of guinea pigs so that you can reuse this knowledge and just adapt it for the guinea pigs. And it works quite decent for a guinea pig, but meanwhile, it turns out that it stopped working actually for the cats and dogs, which is a little bit weird, and we were trying to figure out what happened here. And what happened is catastrophic forgetting. And catastrophic forgetting is something that we can show in a nice graph like here, which actually presents what we just said. So assuming that we have 2 tasks, so first task is training the classifier on cats and dogs, you quite quickly get the level that is very nice accuracy, but the model doesn't know anything about guinea pigs. And then you take a second task and you train them sequentially. So right now, the model gets super on the guinea pigs, but it forgets about everything about cats and dogs. And it's the most important thing, like, which continual learning tries to address. So let's come back to our example. So, okay, another idea. Let's train our model from scratch. So we just trained this initial classifier not so long time ago. We still have the pictures of the cats and dogs and the guinea pig. And let's just train a neural network from scratch and do it. Does it work? Yes. Does it solve the problem? It's actually the best solution to this particular problem. But there are some issues if we are going back to our initial problem. So first of all, it would mean that we need to keep all of the data the whole time. So if you have the data of the patients, you cannot keep the data forever because maybe at some point you'll want to retrain a model. If you are working with like bigger models, there is also significant cost of computations and storage if you like to train them always from scratch. Connected with that carbon footprint, and there is also, when training big models, there's a lot of time needed to doing that. And you don't always have this time or don't always have the money for the computations. So this is where continual learning comes to play. And the main idea behind it is that we should be able to train machine learning models incrementally in a way that they adapt to the ever-changing conditions, but without forgetting what they learned before. Moreover, they should be able to actually reuse that knowledge, what they had before, and build on top of that, like we humans do. And it is not a coincidence that most of the continual learning methods are inspired by biology and how our brains work. And learning from experience is actually also considered one of the key aspects of intelligence. So we can present it as well on a graph. So what we would like to achieve is actually stateful training, meaning we train the model once, as we see on here below, and then just use small batches of data without touching the first data set, instead of like using the whole data the whole time or using some sliding windows. So we'll analyze now 3 main families of the methods that are used in continual learning, starting with the regularization-based approach, which is actually the easiest one. So the idea here is that we can just penalize the model if it's changing the parameters which are crucial for the previous task. So it relies on the idea that if we have a neural network, it's being trained, so it has the weights there. Actually, when we train it on a new task, it's adapting all of these weights. So it's adapting also the ones that were super important for the previous tasks. So the idea here is that we'll just try to prevent the model from changing the ones that were super important for the previous tasks. What's the inspiration here? It's actually quite interesting because there were some experiments done on mice where mice were learning some new skills. So in the moment where mice were learning new skills, they have the neurons being connected, so creating the synapses. And when the skill was learned, the synapses were being protected by the brain, meaning they got less plastic, they were not interacting with the different neurons. And in the moment when this connection got cut, the mice forgot this skill. And this is actually what we are trying to recreate as well in neural networks by protecting this kind of connections that were important. How do we do that? Well, we actually just add some regularization term to our loss function in the neural network, and it's weighted by the parameter importance. How do we know which of the parameters were important? Well, there are also separate methods, such as Fisher information matrix, where we can just calculate which of the weights in neural networks are important for a given task. Issue? Well, the forgetting is not fully eliminated, and it works better when we're having the similar kinds of tasks. So, for example, changing data distribution. Another approach here is using the memory-based methods. So the idea here is that we can just keep some of the data in memory and revisit them later. So just to remind the model, hey, you still need to do this task well because that's important too. And the inspiration here comes from sleep. So whenever we are sleeping, our brain is still working and consolidating our memories. So it's also using the replay method so that we stabilize and create new skills or our memories. What's the issue with this approach? Well, first of all, we cannot put just everything into the memory buffer. And another one is data privacy. I mean, still, we cannot just put the patient's data into the memory buffer forever and just keep using that. But quite interesting subcategory is, when it comes to the data privacy, we can use generative models. So we can just take this data, generate like super similar ones, and put these ones into memory buffer and have no issues with the data privacy. And this is one of the popular methods used especially in the last year. And the third one are the architecture-based methods. So the idea here is that we'll be adapting the architecture of our neural network whenever we're learning new skills. So the inspiration for that is the neurogenesis. So also our brain, when you're learning new skills, can generate new neurons, especially in hippocampus, so that it prevents forgetting and so that it doesn't interact with too many different connections and have more, let's say, space to create the new skills. It's also quite interesting. We're going to come back to this method as they also got new directions right now. But usually it assumes that the boundaries of the task are quite clear. But we'll also see in one of the last slides that there are some newer approaches to this as well. So in the third act, let's combine what we learned about continual learning and how it helped us with the FCD issue. So right now, we learned no mistakes, so we adapted our data distribution to better mimic the real life. So right now, FCDs are just 30, so they will consist in 10% of the cases. We have 150 normal MRIs and 120 non-FCD pathological MRIs. And we divided them into 3 data sets, each of them consisting of 100 MRIs. Because our data distribution has changed, we decided to use the regularization-based approach, specifically the elastic weight consolidation. So we calculated which of the weights were important, we kept them, we penalized the model for changing them, and we trained the model on the new distribution. Let's take a look of how did it work. So we analyzed this in a few phases. So first of them is what we discussed in the first act. Then we took the first data set, so the first 100 MRIs. And first of all, we evaluated them against the model that we trained at the first stage. Then we followed two training strategies. First of them, because actually we wanted to compare how continual learning works, but we also wanted to see, compared to the approach when we would train everything, like on all data, would there be any significant differences? So the first approach is, let's say, this traditional one. So we just take all of the data that we have. We trained our model further, and we got a model that we called a little bit fancy because we also published a scientific paper about it, but let's just call it all data model. And in the second strategy, we used continual learning, so we gave to the model just this 100 MRIs. It hasn't seen any other data at all. We took the base model from that we trained in the first act, and we created a model, let's call it continual learning. In the second phase, again, we evaluated the data right now with the 3 models that we have. We put the results away, we wrote them down, and again, we repeated the same strategy, meaning we gave to the model all of the data that we have. So the baseline data set, the data set number 1, and right now this new data. Again, we trained it against the base model. We got the new all data 2 model. And here for the continual learning, we just used the data set number 2. So we didn't show it again, this data set number 1 or baseline. It was just this 100 MRI series. We trained it based on this continual learning 1 model and created the next version of it. And in the first stage, we could just evaluate the data so that we could have reliable results. Speaking of results, what did we get? Actually, the results were very interesting. Because again, in the baseline model, so the one that we trained in the first act, we managed to collect 8, and 9, like each time from 10, FCDs correctly, which is really good results. But again, the specificity, so we're detecting quite many false positives. In the model that we trained on all the data we had, we got 8 out of 10 and 10 out of 10, which is really great. And we managed to decrease significantly the amount of false positives. And in the continual learning method, we got 8 and 9, which is also very good results. And we managed to decrease the false positives significantly better. So again, we analyzed what happened here. And we saw that in this false positive that still stayed there, our model reacted mainly to the other brain pathologies. So if we were about analyzing just normal data against FCDs, we even could increase the specificity to 90%. But yeah. And we saw that as the training progressed, we also were able to work against this tendency to detecting the FCDs in a specific part of the brain. So what were the conclusions of this part? We managed to get similar level of sensitivity in both of the approaches on the all data and continual learning. We got significantly higher specificity, and what is not so obvious in here, but super important, is that this version of the model using continual learning will be much more robust for further distribution changes. Because if you think about it, it's one of the classical examples of imbalanced data set, meaning we have a class that is always in minority. So if we would just keep training the model, at some point it will be more beneficial for it to say always there is no FCD in there, and it would be 90% or even more right. So it's quite interesting conclusion that we came here, that is training it on 2 specific tasks. So first of them, try to get very well into recognizing these features for this imbalanced data set, and in the next rounds, adapt it to the new data distribution while still keeping the important features for this, let's say, a less frequent class. So our model is considered as useful for daily clinical practice and early detection of FCDs. As mentioned during the keynote yesterday, we are far away from like saying, hey, this model will take the work of radiologists or epileptologists or whatever. It's completely different. Like, we would like to create a model, to create a solution that would be useful for example, for radiologists, neuroradiologists, people who are not super experts like in epilepsy, but just to help increasing the chances that people get the right diagnosis. Meaning, because right now, the majority of the FCD patients that get never the right diagnosis, they don't know they have it because there are too few experts doing that. If you would like to know more, we published 2 papers. If you would like to get, I'm not sure if ResearchGate doesn't want you to pay for that, but if you would like to read it, you can reach out and I can send it to you. But let's take a look like, what can we take with us for like daily praxis in different cases? Like, I know I explained to you some medical use case, probably the majority of you is not working in there, but continual learning is really commonly used and should be used whenever working with machine learning in production. Specifically, usually when you're working with privacy-first environments, so any kind of GDPR, medtech, whatever, when you have strict requirements, so cannot store the raw data in there for long term. In any kind of dynamic environments, so whenever you do personalization, finance, streaming data, so whenever the data is changing very frequently, such as e-commerce, fraud detection, you don't have time for training these models every time from scratch. Anomaly detection is also quite an interesting use case because, first of all, the data can change, like the sensor readings from the machine, they will change a little bit over time. But the imbalanced data set aspect here, it's also always the minority class. So it's also interesting in the meaning that I mentioned to you for us with the FCDs. You could also train the model, first of all, on the features that are there for the anomalies, and then adapt it to the changed data set. But a takeaway here is that continual learning is actually a strategical architectural choice for any production machine learning. Because the data will always evolve. There are also very frequently the privacy issues and also connected with it high retraining costs. And talking about it, probably some of you have been thinking, well, like training big models, frequently changing data, high computational costs. Is it being used in LLMs? Like, it could fit perfectly, right? Well, the truth is that according to any information that I read, and also last year there was a Y Combinator conference when Andrei Karpathy was saying exactly the same thing, that none of the big players is using continual learning yet. Why is that? Well, actually, if you were into any of the talks about how do LLMs work, you probably know that LLMs are not trained as one process. Like, you have many stages. You have pre-training, instruction tuning, alignment, and for each of these things, you could do separately continual learning. And it turns out that in the moment when you change one thing, it also influences the other ones. So it's not so easy to adapt it and to deliver on that. But I think it's also quite interesting, and there are for sure many approaches being done. There are also some open source repositories where people are collecting informations and trials on a smaller scale, where they are actually trying to implement continual learning in there. Because when you think about the main idea here is, like, we want to develop systems who can adapt to ever-changing conditions and learn based on experience without forgetting. I mean, it sounds really like something which is super needed if you want to build AGI or whatever kind of intelligent systems. And there is also some new directions coming. So one of them was released in November 2025 by Google Research called nested learning. So it is a new machine learning paradigm for continual learning, and I think it's super, super interesting, even though I didn't hear about it too much even in my bubble, even though I'm following it quite a lot. But what's the idea here? So usually when we talk about deep learning, we have like neural network architecture, and then we have optimizers. So we treat them as two completely separate things. And what the researchers from Google say, well, they are actually connected. Like, we shouldn't treat them as separate things. We actually should use them, so instead of having one big problem that we got optimized, machine learning and deep learning should actually be solved as nested learners. So we should have a few training cycles, so a few optimizations, which are together creating one bigger learner. Another interesting thing is the concept of continuum memory system. So it means that when we train the models and we want to keep some of the things in memory, we should adapt them in two speeds. So some of them should adapt very fast, and some of them take slower time. So not sure if any of you read the Thinking Fast and Slow of David Kahneman. Like, then you maybe also have like similar kinds of thoughts that, hey, that sounds totally like that. So if you haven't read that, it's quite hard book to read, but the concepts are quite interesting. And David Kahneman, he also got Nobel Prize, so it's definitely a good author to read. Yeah, so this is like very similar concept, although they don't mention it directly in here, but it's also inspired even more about how the human brain is working. And another interesting fact here is that they are also like trying to learn based on, for example, surprises. So whenever the model sees something that is surprising, like it expected it to be this result, but actually in reality it's something different, it saves it, and it also uses it for the further learning to adapt based on this surprises even more. Another interesting thing are the new optimizers. So it relies mainly on the fact that actually we usually in deep learning we have just one function that is optimizing, but they say, hey, why shouldn't the optimizer learn as well? So it should be also part of this nested learner, so it should also optimize and adapt based on the data. And interesting thing here is that they even created a proof of concept for the self-modifying architecture, which got quite promising results. So I think it's still like in a research phase, but it's definitely going to have some interesting further developments. So if you would like to read the paper, here is the QR code. And yeah, this is also something just to sum up. So these are two posts from Google DeepMind researchers. So also probably people who worked on the nested learners before. So they are claiming that this year is going to be the year of continual learning. So agents we already have, but continual learning is also going forward. And yeah, if we manage to deliver any of these promises, I think it's going to be super, super interesting. So with that, thank you a lot. I hope you learned something, and thanks for your attention, and enjoy the rest of the conference.